Okay, so the next type of similarity shortcut we'll talk about is SAS similarity, or side angle side similarity. And this says that if you have two sides of one triangle and they're in the same ratio as two sides of another triangle, and the angles between those sides are congruent to each other, then the triangles are similar. So that's kind of a mouthful. So let's look at an example to see what that means. Okay, so I've got a triangle here, and I have two sides of the triangle. So I can find the ratio of those two sides to each other. So the ratio AB over AC is going to be 2 over 3. All right, I have another triangle, and I know two sides of this triangle. So let me find the ratio of those two sides. So DE over DF equals 4 over 6, which is also equal to 2 over 3. Okay, so I have that the ratio of two sides in the little triangle equals the ratio of two sides in the big triangle. That's what the first part of this theorem is saying. So two sides of one triangle are in the same ratio as two sides of another triangle. Okay, so given AB over AC equals DE over DF. Whoops. Okay, that alone isn't enough. We also need the angle piece. So we've got these two sides. They're in the same ratio as each other. We also have that the angles between the two sides are congruent. So we also need that piece. And angle A congruent to angle D. Now we have enough to conclude similarity. So we need that the ratios are equal and the included angles are congruent. So now I can conclude from this information that triangle ABC is similar to triangle DEF. And with that, I get everything that comes with similarity. So now I know that their remaining corresponding angles are congruent to each other. So angle B congruent to angle E, angle C congruent to angle F, and I know that all their corresponding lengths are in constant ratio with each other. Okay, so let's see how we could use side angle side similarity in a problem. Let's do an example. All right, we're given this figure. It has some lengths labeled on it, and we want to find BC, given that the perimeter of this triangle is 20. All right, so we've got three triangles going on in this figure. We have this little one, we have this medium triangle, and then we have the big triangle. So I'm looking for triangles that I know things about. This little triangle, I know two sides of that little triangle, and the big triangle, I know two sides of that triangle. So maybe I have enough for side angle side similarity. Sometimes when the triangles are overlapping in a figure like this and their orientations are changed, it can be a little hard to see which sides are corresponding to each other. So I often like to redraw them with the same orientation. So let's say I redraw our little triangle, BCA, and label the sides 4 and 6. And then I draw our big triangle with that same orientation. So the same orientation would then be D to B to A. So it would look like this. D, B, A. This side is 6, and then DA is 9. Okay, and let's also note that these triangles are sharing an angle, right? They both have angle A. So on our redrawn figures, I know that this angle is congruent to that angle because it's the same angle. It's congruent to itself. Okay, so from here, let's start, let's set ourselves up for side angle side similarity. I know that the ratio BA over CA is 6 over 4, which is 3 over 2. And on our big triangle, I know that the ratio DA over BA is 9 over 6, which is also 3 over 2. So, we have that BA over CA is equal to DA over BA. So we have two sides of our little triangle being in the same ratio as two sides of our big triangle, and we know that angle CAB is congruent to angle BAD, which is the angle between our two sides, right? So we can therefore conclude that our triangles are similar. Triangle BCA is similar to triangle DBA by side angle side similarity. Okay, so what can we get from there? We know that the ratio of corresponding lengths is constant. So I could say that the ratio of, let's say, DB to BC, which is what we want, would equal the ratio of DA over BA, so 9 over 6, 3 over 2. Okay, so there's one equation that has BC in it. Can I write another equation that has BC in it? Well, we know that the perimeter of triangle BCD is 20, so here's BCD, its perimeter is 20, so that means that DB plus BC has got to equal 15, since the remaining side is 5. So my other equation is that DB plus BC equals 15, and that's from the perimeter. Okay, so now I've got two equations that have DB and BC in them, and I bet I can solve these for BC. So from here, I get that DB equals 3/2 BC, and then let's substitute that into this equation. So 3/2 BC plus BC equals 15. That means 5/2 BC equals 15. And if I solve that for BC, I should get that BC equals 6. Okay, so that's a quick overview of side angle side similarity and an example of how to use it to solve a problem. Um, Again, there's an exercise in your textbook, I believe, let's see, section 5.3, that goes through showing why side angle side similarity works. So if you're interested in that, I would check out that exercise in your textbook.